In this video, we're going to study the relationship between temperature and kinetic energy. And we know that as temperature increases, the molecules move faster. And therefore, the kinetic energy increases. Now, the relationship is KE is 3/2 kBT, where KB is a constant, 1.38 times 10 to the minus 23rd joules per Kelvin. This temperature has to be in Kelvin. Remember I said if it's a delta T, it could be in Celsius or Kelvin, but if it's a T, it has to be in Kelvin. Now, I want to show you what a graph of that would look like if I look at temperature and kinetic energy. Okay, this is a direct relationship. There's no squareds of the temperature. It's not 1 over the temperature or anything like that. It's just a straight direct relationship, so it's going to look like that. Now, the average kinetic energy of the molecules in a sample of 2 moles of gas we're going to find first, and then the total internal energy of the gas. So first, the kinetic energy is 3/2 kBT. It is 3/2. KB is this 1.38 times 10 to the minus 23rd joules per Kelvin. And then the temperature is 30 Celsius, so the temperature is 30 plus 273 is 303 Kelvin. Okay. And when I multiply that together, I end up with a kinetic energy of 6.27 times 10 to the minus 21 joules per molecule. Now that's the average kinetic energy of each molecule. Some of the molecules will be going a little faster, some will be going a little slower. This is just the average. Now, the second part asks for the total internal energy of the gas. I'm going to give you a definition here. We're going to use the letter U to stand for total internal energy. Okay, the internal energy is the energy of the molecules. We could get that by doing potential energy plus kinetic energy of each molecule, but this is 0, PE equals 0 for an ideal gas. Okay, here's why. The reason if I lift a weight, I'm giving it potential energy is because it's attracted back to the ground. If I let go of it, it will fall down to the ground. There's no attraction between the molecules and ideal gases, so it doesn't take any energy to move them apart from each other. So I'm not storing any potential energy in there. So the total internal energy just equals the total kinetic energy of all of the molecules. So what we need to do is find out how many molecules there are. All right, in order to do that, we use this idea. N, or capital N, stands for the number of molecules. Well, that's related to the number of moles. It's going to be the number of moles times Avogadro's number. And you should remember from chemistry that Avogadro's number is 6.02 times 10 to the 23rd molecules per mole. So, in this particular example, our number of molecules is going to equal 2 moles, because that was given, times 6.02 times 10 to the 23rd molecules per mole. And that's going to give me a value of 1.204 times 10 to the 24th molecules. Now, to get the total internal energy, remember, it's just the total kinetic energy equals the kinetic energy per molecule times the number of molecules. So up here, we found the kinetic energy of the molecules was 6.27 times 10 to the minus 21st joules per molecule. And we just found the number of molecules is 1.204 times 10 to the 24th. And that's going to give me a value of 7549 joules for the total internal energy of the gas. There's an easier way to do this, which we'll deal with later, but this is doing it by definition. Total internal energy is equal to the total kinetic energy of the molecules. Now, temperature and speed of the molecules, there's an equation for this on the reference table. I don't think it's that important, but since it's there, we have to cover it. Now, we know that kinetic energy is equal to 3/2 kBT. Now, I want to get speed in here, velocity. I can do that by replacing the kinetic energy with 1/2 mv squared. Now I'm going to solve this for velocity. So the 2's would cancel here, and I would divide by m. So I would get v squared is equal to 3 kBT over m. And then to get rid of the squared, I take the square root. So there's an equation. You might have to use it on the exam. Now, this is a particularly difficult example, but I think it's kind of interesting as well. There's a mixture of hydrogen and oxygen gas at the same temperature, and I want to know the ratio of the speeds of the hydrogen molecules to the oxygen molecules. The hydrogen molecules are smaller and lighter. They are going to move faster. So we're going to use this equation. V is V is the square root of 3 kBT over m. So we need to find the mass of the molecules. Now, it gives me the mass of the oxygen molecule is 32 atomic mass units, and I need to convert it into kilograms. So we're going to do this for the oxygen over here, and we're going to do it for the hydrogen over here. Now, the mass is 32 AMUs. And it says here that each AMU has a mass of 1.67 times 10 to the minus 27. So 1.67 times 10 to the minus 27 kilograms per AMU. And that's going to give me the mass in kilograms. And it is going to be 5.34 times 10 to the minus 26 kilograms. Now I'm going to plug into this equation. V is square root of 3 kBT over m. That's the square root of 3. kB is the constant, 1.38 times 10 to the minus 23rd. Now our temperature is 20 degrees Celsius. That's 293 Kelvin. So times 293. And divided by the mass that we just found, 5.34 times 10 to the minus 26. Then we end up with a value of a velocity of 477 meters per second. So that's the velocity of the oxygen molecules. Now for hydrogen, follow the same process. The mass is going to be 2 AMUs times 1.67 times 10 to the minus 27th kilograms per AMU. And that gives me a mass of 3.34 times 10 to the minus 27th kilograms. Then I'm going to plug into the velocity equation here. So it's 3 times 1.38 times 10 to the minus 23rd times the temperature was 293 divided by the mass we just found, 3.34 times 10 to the minus 27th. When I do that, I end up with a velocity of 1906 meters per second. So the hydrogen being lighter is traveling faster, because that's the velocity of the hydrogen. Now, the question is asking for the ratio of the velocity of the hydrogen molecules to the velocity of the oxygen molecules. So VH2 over VO2 is equal to 1906 divided by 477. And if you do that, you end up with 4.0. So the hydrogen molecules are going 4 times as fast as the oxygen molecules. The reason I find it kind of interesting is which we find more of on Earth. We find a lot more oxygen on Earth than we do hydrogen. The reason why, the hydrogen's moving faster, and therefore it can escape the Earth's gravitational pull. Remember, this 1906 is only the average velocity. Some are going faster than those will escape or can escape the Earth's gravity. If you look at Jupiter, it has a lot more hydrogen for 2 reasons. It's bigger, so it has more gravity, and it's colder. Being colder, the molecules are moving around more slowly, so the hydrogen can't escape. And that's why the inner planets like Earth don't have a lot of hydrogen, but the outer planets, the big gas giants, do have a lot of hydrogen.